Section 1 Introduction. We're here to introduce you to a fascinating development in the field of natural language processing, NLP. The game changer is the advent of transformer-based large language models, LLMs. By increasing the size of these models and the pre-training data, we've seen significant improvements in their capabilities and efficiency. They've even started to show abilities like multi-step reasoning and following instructions. However, complex multi-step reasoning still poses a challenge for even the most advanced LLMs. One promising solution is process supervision, which involves verifying each step of the reasoning process. Techniques like chain-of-thought prompting have been developed to create a logical sequence of reasoning steps, increasing the chances of successful decoding. Taking inspiration from human problem-solving, we've proposed a new technique called step-back prompting. When humans face difficult tasks, we often step back and abstract the problem to understand the underlying concepts and principles. This helps us avoid errors in our reasoning. We believe that teaching LLMs to do the same could improve their performance. Abstraction is a key cognitive skill that allows humans to process large amounts of information and derive general rules and principles. For instance, Kepler was able to distill thousands of measurements into 3 laws of planetary motion. In decision-making, abstraction helps us see the bigger picture. We're exploring how LLMs can use a 2-step process of abstraction and reasoning to tackle complex tasks. The first step is to teach the LLMs to abstract the problem and identify high-level concepts and principles. The second step is to use these concepts and principles to reason through the problem. We've used a few short exemplar demonstrations to implement step-back prompting on LLMs. We've tested this technique on a range of tasks involving domain-specific reasoning, such as physics and chemistry, knowledge-intensive question answering, and multi-hop common-sense reasoning. We've seen significant performance improvements, demonstrating the effectiveness of step-back prompting for complex tasks. However, some tasks remain very challenging. Both PaLM-2L and GPT-4 only achieved around 40% accuracy on time QA and musique. While chain-of-thought prompting led to minor improvements on a few tasks, step-back prompting improved the performance of PaLM-2L across the board. Our analysis shows that step-back prompting has strong performance improvements over other prompting techniques. We also found that step-back prompting fixed a large portion of the base model's errors while introducing a small number of new errors. Most of the errors made by step-back prompting were due to the LLM's inherent limitations in reasoning capabilities, while abstraction skills were relatively easy to teach. Step-back prompting is based on the observation that many tasks contain a lot of details, making it hard for LLMs to retrieve relevant facts. For example, a physics question about the pressure of an ideal gas or a question about a Stella Leopold school history can be difficult to answer directly. In both cases, asking a step-back question at a higher level of abstraction can help the model solve the problem effectively. In summary, step-back prompting involves 2 simple steps: abstraction and reasoning. First, we prompt the LLM to ask a generic step-back question about a higher-level concept or principle. Then, based on the facts about this concept or principle, the LLM can reason about the solution to the original question. We call this abstraction-grounded reasoning. We've conducted an empirical study of step-back prompting on a range of challenging tasks, and we're excited to share the results with you. Section Summary. The introduction highlights the advancements in natural language processing, NLP, achieved through large language models, LLMs, like transformers. However, complex multi-step reasoning remains challenging for these models. To address this, the authors propose step-back prompting, which involves teaching LLMs to derive high-level abstractions and principles from specific examples, and then using reasoning to solve the original question based on these abstractions. Experimental results show significant performance improvements across various tasks, demonstrating the efficacy of step-back prompting in tackling complex reasoning tasks. Section 3 Experimental Setup. In this section, we'll outline our experimental setup, including the tasks and models we used, our evaluation method, and the baseline methods we considered. We experimented with a variety of tasks, including STEM, knowledge QA, and multi-hop reasoning. For the STEM task, we used the MMLU dataset, which includes benchmarks across various domains to test a model's language understanding. We focused on the high school physics and chemistry sections due to the deep reasoning required. For the knowledge QA task, we used the time QA and situated QA datasets, which contain complex queries requiring time-sensitive knowledge and the ability to answer questions within specific temporal or geographical contexts. For the multi-hop reasoning task, we used the music and strategy QA datasets, which require complex reasoning and strategic thinking. We used two state-of-the-art language learning models, LLMs, for our experiments, PaLM-2L and GPT-4. We also used a variety of baselines with an instruction-tuned PaLM-2L model. Evaluating these models can be challenging, as traditional metrics like accuracy and F1 score can struggle to capture the nuances of the long-form answers these models generate. Instead, we used the PaLM-2L model to evaluate the equivalence between the target answers and the model's predictions. We considered several baseline methods, including PaLM-2L, PaLM-2L one-shot, PaLM-2L plus COT, PaLM-2L plus COT one-shot, PaLM-2L plus TDB, PaLM-2L plus RAG, and GPT-4. Each of these methods involves different strategies for querying the model and providing it with context. We then evaluated our method, step-back prompting, on STEM tasks. This involved teaching the model to understand and apply physics and chemistry principles and concepts, such as Newton's first law of motion, the Doppler effect, and Gibbs free energy. Our results showed that step-back prompting significantly improved model performance, achieving state-of-the-art results. However, we also found that the model's performance was robust against the number of demonstration examples used, and that most errors occurred during the reasoning step. In conclusion, our experiments showed that step-back prompting can significantly improve model performance on tasks requiring complex reasoning. However, the reasoning step remains a bottleneck, and further work is needed to improve the model's reasoning and math skills. Section Summary. In this section, the authors describe the experimental setup of their study. They experiment with three different tasks: STEM, knowledge QA, and multi-hop reasoning, using various datasets. They use state-of-the-art language models such as PaLM-2L and GPT-4, along with different baseline methods for comparison. They evaluate the models using a novel evaluation metric that involves few-shot prompting. The results show that their step-back prompting method significantly improves model performance, surpassing the baseline and achieving state-of-the-art results. Error analysis reveals that errors mainly occur during the reasoning step, highlighting the challenge of complex reasoning tasks. Section 5: Knowledge QA. In this section, we're going to discuss our evaluation of a method we call step-back prompting, in the context of question-answering tasks that require a deep understanding of factual knowledge. This type of question answering, known as knowledge QA, has proven to be a tough nut to crack for language learning models, LLMs. We'll start by outlining our experimental setup, then move on to the results and analysis of our step-back prompting method. We tested step-back prompting on two knowledge QA benchmarks, time QA and situated QA. The first step was to teach the LLMs how to abstract information. For example, the LLM was asked to generate a step-back question like, "What was Estella Leopold's education history?" using a few examples as guidance. Given the fact-heavy nature of these questions, we combined step-back prompting with a method called retrieval augmentation, RAG, to help the LLM retrieve relevant facts. These facts then served as additional context to guide the final reasoning step. When we tested our models on the time QA test set, the baseline models of GPT-4 and PaLM-2L scored 45.6% and 41.5% respectively, showing how challenging the task was. However, when we added regular retrieval augmentation, RAG, to the baseline model, the accuracy improved to 57.4%. This highlights the importance of factual knowledge in these tasks. When we combined step-back prompting with RAG, the accuracy on time QA jumped to an impressive 68.7%. We also divided the time QA test set into easy and hard difficulty levels. As expected, all methods performed worse on the hard segment. While RAG improved the easy accuracy from 42.6% to 67.8%, the improvement on the hard accuracy was much smaller, from 40.4% to 46.8%. This is where step-back prompting really shone, improving the hard accuracy to 62.3%, outperforming GPT-4's 42.6%. On the situated QA benchmark, we saw a moderate increase in quality from 54.3% to 61% when using step-back prompting combined with RAG. We also conducted an ablation study to understand the impact of the number of examples used in the demonstration. The results showed that the performance of step-back prompting was robust, regardless of the number of examples used. When we analyzed the errors made by step-back prompting, we found that more than half of the errors were due to reasoning errors, while 45% of errors were due to failure in retrieving the right information. This reflects the difficulty level of the time QA task. We also evaluated step-back prompting on the challenging multi-hop reasoning benchmarks Musique and Strategy QA. The baseline performance of PaLM-2L and GPT-4 was low in Musique, but stronger in Strategy QA. However, step-back prompting with the power of abstraction produced the best performance of all methods, significantly outperforming GPT-4 on both tasks. Section Summary. In this section, the authors evaluate the effectiveness of step-back prompting on question-answering benchmarks that require extensive factual knowledge. They find that combining step-back prompting with retrieval augmentation, RAG, significantly improves the accuracy of the models, especially on the time QA benchmark where the accuracy reaches 68.7%. The authors also observe that step-back prompting performs well on the Musique and Strategy QA benchmarks, outperforming GPT-4 with accuracies of 42.8% and 86.4% respectively. Section 6.2 Analysis. In our analysis, we've noticed that our method, which we call step-back prompting, combined with RAG, can correct about 15.4% of the base model's incorrect predictions. However, it also introduces about 6.1% errors. Additionally, when we combine step-back prompting with RAG, it corrects about 12.7% of the errors that RAG alone would make, while only introducing about 4.4% new errors. We've included a more detailed analysis in the appendix. In our discussion, we found that abstraction is a powerful tool. It allows us to simplify complex tasks by removing unnecessary details and focusing on the main concepts and principles. This is the basis of our step-back prompting method. It divides complex tasks, like knowledge-intensive question answering, multi-hop reasoning, and science questions, into two separate steps: abstraction and reasoning. Our experiments show that it's relatively easy to teach language learning models, LLMs, like PaLM-2L the skill of abstraction through efficient demonstrations. Once the LLMs understand the main concepts and principles, they can use their inherent reasoning abilities to find the solution. This method reduces the likelihood of reasoning failures in the intermediate steps and improves performance on a variety of complex reasoning tasks. However, we've also found that reasoning is still a difficult skill for LLMs to learn. Even with the simplification provided by step-back prompting, reasoning remains a common failure point. Also, abstraction isn't always necessary or even possible. For example, for a simple question like, "Who was the President of the United States in 2000?" there's no need for abstraction. Similarly, for questions like, "What is the speed of light?" abstraction wouldn't make a difference. Our work on step-back prompting is related to other research on prompting and decomposition. For instance, few-shot prompting has greatly improved model performance across various tasks without needing to update any model parameters. Our method is similar to chain-of-thought prompting and Scratchpad due to its simplicity and universal applicability. However, our focus is on abstraction, which is inspired by the human ability to perform complex tasks by stepping back and looking at the bigger picture. Our work also relates to recitation-augmented language models. But unlike these models, we explicitly perform step-back and abstraction, with optional use of retrieval augmentation depending on the task. In terms of decomposition, breaking a task into simpler tasks to solve the original task has been an effective way to improve model performance. Our method, step-back prompting, differs from decomposition as it makes the question more abstract and high-level, rather than breaking down the original question into smaller parts. Also, abstract questions like, "What is the employment history of person X?" are often generic and can correspond to many specific questions. This is different from decomposition, where there are multiple subproblems necessary to answer a given question.